Welcome back, Year 12s. We've only got 2 videos left on Chapter 6. This is the second last video covering the general solution of trigonometric equations. This is where you see the letter n pop up to represent an integer. And the reason why we need general solutions is trigonometric equations have infinitely many solutions unless you restrict your domain. And that's because if you add 2 pi, you get an identical angle. So we need some way to capture all possible solutions without having to write them all down and figuring out a pattern. So I'll do this with some examples. And first, I'd like to consider the equation sine of x equals a half. Using our knowledge of exact values, the inverse sine of a half is pi on 6. So I know that pi on 6 is a solution. Now, please note that there's another solution. There's 5 pi on 6 as well, but you're only going to get this particular solution if you use the inverse sine function on a calculator. And that's because, by definition, inverse sine has range from negative pi on 2 to pi on 2. So if sine is negative, you'll get a negative angle. If sine is positive, you'll get a positive angle. So if we want to get the second family of solutions, we'll need to do pi minus the inverse sine of a half, which gives me 5 pi on 6. And that's this red angle here. So this is quadrant 1, and this is quadrant 2. Quadrant 1, quadrant 2. And so immediately I can write down x equals pi on 6 plus 2n pi. That's one family of solutions. But I can also say x equals 5 pi on 6 plus 2n pi. Now what's n? N is an integer. And the integers are all the positive and negative whole numbers. So I'll say negative 2, negative 1, 0, 1, 2, dot, dot, dot in both directions. And z is the set of integers. So what we're saying here is start at pi on 6 or 5 pi on 6 and rotate by multiples of 2 pi, clockwise or anti-clockwise, as many times as you like, and you'll get back to the same position on the unit circle. Okay, so that's one way to describe the solutions. Now there's another way as well. See how there's 2 families here? There's a very slick way to combine these 2 families into one family, or one list. And that's to do the following. It's not immediately obvious. Essentially, what we want to do is say, okay, suppose I count n pi. If n is even, I need to add pi on 6. If n is odd, then I want to subtract pi on 6. The way we do this is to say minus 1 to the power of n times pi on 6, and then add that on. So what's happening here is if n is even, minus 1 to a power of an even number is positive, so I'll add pi on 6. But if n is odd, minus 1 to the power of an odd number gives me negative 1, so I'll end up subtracting pi on 6. And again, n is an integer. Please note that when you write a general solution, you must write n as an element of z. If you don't write this, you are not specifying what the number n means, and you don't want to leave it up to your marker to guess. Because if they have to guess, you haven't demonstrated your understanding, and you likely won't get the mark. So please make sure, absolutely sure, that you write this at least in your final answer in your exams. And general solutions can appear in exam 1. Okay, so that's sine. Let's look at cosine now. So this time I've given you cosine of x equals root 3 on 2. And so here, using our knowledge of exact values, we can say that cosine of pi on 6 is root 3 on 2. So that means the inverse cosine of root 3 on 2 is pi on 6. Now please note, inverse cosine does not have the same range as inverse sine. So if your cosine is positive, you'll get an angle between 0 and pi on 2. If your cosine is negative, you'll get an angle between pi on 2 and pi in quadrant 2. So quadrant 1 gets me to pi on 6. Quadrant 4, I either need to do 2 pi minus pi on 6, or I could just say, take a negative angle. And that's what I'm going to do, because it's actually simpler to do that. So that's this part here. Take a negative angle to rotate clockwise rather than counterclockwise. So essentially what we're saying here is there are two families of solutions. I can start at pi on 6 and add 2n pi, or start at negative pi on 6 and add 2n pi, where n is an integer. Now, a simpler way to write this is as follows. Start at 2n pi and plus or minus pi on 6. So it's actually easier than sine. Cosine equations are easier to write down a general solution for. Now, would this work in quadrant 2 and quadrant 3? Yes, because then you'd be on this side of the unit circle. Again, there's symmetry about the x-axis. Okay, so this is quadrant 1, and this is quadrant 4. Okay, let's do tan now. So this is quadrant 1, this is quadrant 3. Now, tan has range negative pi on 2 to pi on 2, not including the endpoints. And that's because tan of positive pi on 2 and negative pi on 2 is undefined. Remember, we had those asymptotes on those graphs. So if tan is positive, I'll get a positive angle. If tan is negative, I'll get a negative angle corresponding to the fourth quadrant. Now, suppose I want to solve the equation tan of x equals 1 on root 3. Here, I would need to use my exact value knowledge. The inverse tan of 1 on root 3 is pi on 6, giving me a solution in the positive part of this range here. Okay, now that gives me the solution in quadrant 1. The solution in quadrant 3 is pi plus the inverse tan of 1 on root 3, which gives me 7 pi on 6. Now, one thing you should be seeing here is every time I add pi, I get another solution. So I could write x equals pi on 6 plus 2n pi and x equals 7 pi on 6 plus 2n pi. But a better way to write this, and I'll say it's more efficient as well, is to recognize that tan has period pi. rather than period 2 pi. So I can collapse both of these families into a single family. A more efficient way of writing this is x equals pi on 6 plus n pi. Start at pi on 6 and add as many multiples of pi, clockwise or counterclockwise as you like, and you will still have a solution. Okay, so in this video thus far, I've shown you the longer way to write it, and then I've shown you the easier way to write it. The reason why I've shown you both is because if you know the longer way, you can figure out the shorter way. But if you've forgotten the shorter way and you don't know the longer way, you won't be able to reproduce this in exam 1. So I'm trying to emphasize things that are easy to remember, which you can use to reconstruct other things that you might not remember as easily. Okay, so you'll notice that I used pi on 6 for all 3 examples. So for sine, it was sine of x equals a half. For cosine, it was cosine x equals root 3 on 2. For tan, it was tan x equals 1 on root 3. Now, on the next page, I'm going to summarize all of this in an abstract way. If you have trouble with the next page, just go back to these 3 examples and replace the angle with pi on 6. And you're back to where we started. Okay? So, now I'm going to be completely general. Suppose I give you the equation sine of x equals some number alpha, where alpha is between -1 and 1. Now, the reason why I've chosen it to be between -1 and 1 is because the range on the sine graph is -1 to 1. So if it's outside that range, there's actually no solution. So I want this to be useful. I want to set this up so that there are solutions to the equation. Okay, so the first solution is going to be the inverse sine of alpha. And then I get a family by adding 2n pi. So that's the first quadrant, assuming that alpha is positive. The alternative is to take pi minus the inverse sine of alpha. That gives me an angle in the second quadrant, and then add 2n pi. So let's say quadrant 1, quadrant 2. Or, more concisely, x equals -1 to the power of n inverse sine of alpha plus n pi, where n is an integer. Okay? Now, things you need to know. Here, I'm assuming if alpha is positive. If alpha is negative, these formulas still work, but you've just got to remember that now you're looking at quadrant 3 and quadrant 4. But the formulas will still work. So why does this work? Well, I don't think you need to fill in the details, but I'll just say the inverse sine of alpha is negative. I'll say is between minus pi on 2 and 0 if alpha is negative, and inverse sine of alpha is between 0 and pi on 2 when alpha is positive. Okay, let's do cosine next. So the family of solutions was, first we had the first quadrant, inverse cosine of alpha, and then add 2n pi. And then we also had the negative of that angle going in the other direction to an angle in the fourth quadrant, plus 2n pi. So again, I'm assuming this is quadrant 1 and quadrant 4 if alpha is positive. Now here we need to be careful as well. Inverse cosine is between pi on 2 and pi when alpha is negative. So no, it's not negative pi on 2 to 0 this time, it's pi on 2 to pi. And that's just a convention that's used. If you take specialist maths or first year university maths, you'll learn why that is. It's just something that we all sort of agree on as mathematicians. And if cosine, it's between 0 and pi on 2 when alpha is positive. Okay. Now, a simpler way to write this is x equals 2n pi plus or minus the inverse cosine of alpha. Notice that I'm being careful to write that n is an integer because that's an important part of the general solution. Okay, finally, we'll say tan inverse of alpha is positive when, I'll start with negative to keep it consistent. So inverse tan of alpha is negative when alpha is negative, and inverse tan alpha is positive when alpha is positive. So again, I'll start by assuming that alpha is positive. The formulas in all three cases, sine, cos, and tan, will continue to work. If it's not positive, you'll just need to adjust your quadrants and just convince yourself that it works. But if you're happy to take it at face value, you can just use these formulas. So first, we have inverse tan of alpha. That gives me my solution in quadrant 1. And of course, I can add 2n pi. Or I can have pi plus inverse tan of alpha. That gets me to quadrant 3. And then I can add 2n pi as well. Now, as we noted in the previous page, I can collapse these two into a single family because tan has period pi. So I can just say x equals inverse tan of alpha plus n times pi rather than 2n times pi. Okay. All right. I think we need to do just a couple more examples just to solidify all of this. So from this point onwards, I will use the short solutions, and I'm just going to make this as straightforward as possible. So let's do the general solution of the following equations. I'll set some up so that they include negative signs as well. Okay. You know what? Let's make them all negative, just because negatives are tricky. So let's start with the inverse cosine of negative root 2 on 2. Remember, cosine inverse gives me an angle between 0 and pi. So I want the second quadrant angle that gives me a cosine of root 2 on 2, well, negative root 2 on 2, and that is 3 pi on 4. So notice I didn't write down negative pi on 4, because by definition, inverse cosine is between 0 and pi. Now, the solution is x equals 2n pi plus or minus the inverse cosine of negative root 2 on 2. So x equals 2n pi plus or minus 3 pi on 4. Done. And if you wanted to, you could combine everything into a single fraction, like so. So 8n plus or minus 3 times pi divided by 4. 8n over 4 gives me 2n. Okay. Sine. So first, remember that inverse sine is between negative pi on 2 and pi on 2. So the inverse sine of negative root 3 on 2 will be an angle in the fourth quadrant, which is negative pi on 3. Okay, since sine of pi on 3 is root 3 on 2, if I take a negative, I get a negative value. So this time, what I want to do is take minus 1 to the power of n times the inverse sine of my angle, of my trig ratio, I should say, plus n pi. So that's negative 1 to the power of n times negative pi on 3 plus n pi. And we can leave it like that. You could choose to put it into a fraction if you wanted to. I guess we will. Okay. I don't think it's necessary to combine it like that, but if you wanted to, you could. Now, you might ask, why did the power change from n to n plus 1? And that's because there's a factor of negative 1 here. So I've just absorbed it again. Why is it minus pi on 3? Because it's minus root 3 on 2. So my first solution with n equals 0 will require me to go down to negative pi on 3. My second solution, where n equals pi, what I will want to do is actually add pi on 3 to get into the third quadrant. And the way that will happen is I'll have minus 1 times minus 1, which gives me plus 1, which results in addition. So it works. It'll take a bit of experience, but you should see that this indeed works. Okay, tan is probably the easiest one. So the inverse tan of negative root 3. So remember, inverse tan is unbounded. You can write inequalities involving infinity. If it upsets you, you could just say inverse tan of x is an element of R. Tan of pi on 3 is root 3, so tan of negative pi on 3 is negative root 3. Okay, so the general solution involves the inverse tan of my ratio plus n pi. So it's just going to be negative pi on 3 plus n pi. And if I want to create some room, what I'll do is I'll say it's 3n minus 1 divided by 3 times pi, where n is an integer. You probably only need to write n as an integer once. You can write it at the end, but make sure you write it. It's easy to forget. If you're scared you're going to forget, just write it on every line, and that way you're safe. Okay, so that's the general solution. Yes, you need to be able to reproduce this in exam 1. I think it'll come with practice, and you probably want to review this during term 2 and term 3. You don't want to be seeing this for the first time in October, since April. So make sure you're practicing throughout the year. Make sure you're looking at checkpoints questions, and you're looking at exam style questions throughout the year. All right, so we've got one video left on chapter 6, which is modeling. Look forward to seeing you then. Thanks.